I learned in my history of math class that many other civilizations way before Pythagoras was around knew this relationship between right triangles. The Pythagoreans are just the ones that wrote it down, so that's why they get credit for it. In a right triangle, the sum of the squares of the length of the legs is equal to the square of the length of the hypotenuse. And I think if I remember correctly with Miss Bai last year, you guys did this little activity with squares where you like cut off the squares to make the a squared plus b squared equals c squared. Do you have any memory of this? I remember her telling me about it. Like she was so excited about doing this because it was kind of a way to see it. And so the big thing is we know the hypotenuse squared is equal to the sum of the bases squared. It matters which one is C, doesn't really matter which one you call A, B, and B, right? Which means if you know 2 to 3 sides, just like we did on the homework, just like hopefully you just did on the homework quiz, you can solve for those. So I didn't give you a ton of these problems today because I feel like we know how to do this, right? Oh wait, look at this. Let me show you this proof. It's not on your paper. There are other types of triangles. So I just want to show you, why did we do geometric mean yesterday? Why did we do that awful stuff? I just want to show you this proof. I didn't put it on your paper, but it's in your book, like if you want to look at it. And just so you know, notice they draw a right triangle. They draw in that altitude. This whole side is C. They just break this up as X and Y. So using the ratios, using the theorems from yesterday, we can say that we can solve A squared is equal to C times Y, because it's always the ratio that we can put up here. And we can say that B squared is equal to C times X, because this is the bigger side of that other triangle. So notice when they do the cross product here, look, what's a really cool way to prove this, that you're not using geometry? Most of the other proofs I've ever seen with Pythagorean theorem use area, like what you did with Miss Bai. But this one says, what if we add these together now, right? What if I said A squared plus B squared? A squared plus B squared equals, and I add these two sides together, CY plus CX. Right, so kind of like when you just add 2 equations for elimination. So I factor a C out of that. Right? I factor C out of that. And what does Y plus X add up to? Y plus X adds up to C, which means you could just replace Y plus X with C. And what's C times C? Oh my gosh, it's the Pythagorean theorem. And it's a really cool algebraic proof of Pythagorean theorem. So I didn't waste my paper on it for you because I knew you really wouldn't care, but I thought it was something cool. Maybe at some point I will put an extra credit problem for you to solve this one. I put a couple questions on here just to remind you. Make sure you look at which ones they give you, right? The biggest mistake people make with Pythagorean theorem is always adding the 2 together, right? Part A is like good old Pythagorean theorem. Because we could just say 4 squared plus 7 squared equals x squared. 16 plus 49 equals x squared. Yeah. So just like we talked about yesterday, we like exact answers here. So when we take the square root of an equation, usually we do plus or minus, think back to quadratic formula. But in a triangle, you can't have a negative side length, so that's why in Pythagorean theorem, we always just take the positive square root. And yes, Garrett, we are going to leave it as a square root of 65, unless that has some perfect squares to take out. We want this and not this. And does 65 have any perfect squares in it? No, it doesn't. And most things in life don't work out so nicely, so that's why you're going to get lots of square roots. Yeah. So I just wanted to do part B here to just remind you, right, if they give you the hypotenuse, I think you all know how to do this because we did it already. If they give you the hypotenuse, right, you're going to have to solve for x. So it's kind of up to you on how you want to do it. You could say x squared plus 8 squared equals 12 squared. Or maybe you just know every time you're going to take the hypotenuse minus the leg squared, and you just automatically start there. But just be careful which one they give you. My kids in pre-cal still make that mistake sometimes. So that's what, 144 minus 64? So square root of 80. So 16 goes into that, right? So we can say square root of 16, square root of 5. That's the answer I want. Exact answers. So I don't know how much you talk about this in middle school with Pythagorean theorem. There are these things called Pythagorean triples, which are just three numbers that work out perfectly in Pythagorean theorem. Chandler should love these. He doesn't like them. It doesn't work out nicely. So in your book, they give you these, right? 3, 4, 5 is a perfect right triangle. Just think about it. If you take 3 squared plus 4 squared, 9 plus 16, is that going to equal 25? And what's really cool is any multiple of 3, 4, 5, right? Think about similar triangles. So if you doubled them all, or you tripled them all, right? Or any multiple, so your book says like anything that's 3x, 4x, or 5x is going to be a perfect Pythagorean triple. And there, again, many years ago, way even before Pythagoras, there were other civilizations that were aware of these triples that would be perfect right triangles. Think about up there building things that they know these triples, they know they're going to get a right angle of this is the other one that I know. I'll tell you, being a math teacher, 3, 4, 5, and 5, 12, 13. Those are the ones that I just have seen a lot. So if I see a triangle where one side's 5 and the hypotenuse is 13, I always know it's 12 because I just have it memorized. And again, any multiple of those will work. Your book suggests that you should memorize these. I think that's silly. It's nice, but I think you can always use Pythagorean theorem. No, it's okay. And definitely, like, that's what I do. And pre-calculus, if that ever shows up, it makes me super happy. It works out really nice for me, and I know that. I'll tell you that I did not remember these two, right? If these two came up, I would have just done Pythagorean theorem, and then it worked out, and I'm like, oh, that works. But those two over there, I don't know why I had those memorized. But again, any multiple of those. So if you want to memorize it, you want to just memorize the basic numbers and then any multiple of those, which makes things a lot quicker if you recognize them. It's kind of cool that those numbers work out. And there's other ones. Right. Then you just do Pythagorean theorem, right? You always just can work it out, and then when it works out nicely, you'll be like, oh, cool, it worked out nicely. Lots of application problems with Pythagorean theorem. Some work out nice, some don't. I guarantee you when you take the PSAT next year, there will be Pythagorean theorem in that test. And so I've done questions like this in my pre-calc class this year. It says, a 20-foot ladder is placed against a building to reach a window that's 16 feet above the ground. How many feet away from the building is the bottom of the ladder? In this example, it gives you the picture. At some point in the near future, I'm not going to give you a picture, and I'm going to want you to be able to draw the right triangle from there, label the sides. But you can see that this is just Pythagorean theorem. And maybe it's a Pythagorean triple. But if you didn't know that, remember that you can always just set it up where the hypotenuse is the ladder. So we would be saying 20 squared minus 16 squared. Or maybe you think 3, 4, 5, right? This is times 4 times 4. So 3 times 4 is 12. Do you get 12 out of that? Right, only the Pythagorean triples work out nicely. So you can. Okay, so here might be the new part, all right? That's all stuff you've done. I don't know, you can tell me if you've done this or not. So, the converse, right? Remember, converse means when you flip the hypothesis and conclusion. So the converse says, if you know that when you add the two legs together squared, that it equals the hypotenuse squared, then you know it's a right triangle, right? If that doesn't happen, it's not a right triangle. So that's a way that you can prove that something's a right triangle without knowing the angle of 7 degrees. But what's also cool about that is you can use that to determine whether the triangle is acute or obtuse without actually drawing the triangle. So, these other two theorems, I feel like they should be corollaries to theorem 8.5, but they're their own theorems, says if you take the longest side of the triangle and you square it, and if it's less than when you add the two legs, right? If it's equal to its right, if it's less than, does it make sense that it should be an acute triangle? If it's less than, not equal to, because acute is less than. But you got to remember to put c squared on this side, or you get messed up. And if you do c squared equals a squared plus b squared, and the hypotenuse squared is bigger than adding the two legs together, then that is a way to prove that a triangle is obtuse. Did you learn that last year? I'm thinking you did, right? Yes, you did. You have no clue. Right. So you have to remember to put c squared first, right? So basically you just compare the hypotenuse to the legs to determine whether it's right, acute, or obtuse. But I thought we should point out, do you know if I give you three numbers, will it always make a triangle? Like if I gave you 1, 2, and 3, and I said 1 inch, 2 inch, 3 inches, is that going to always make a triangle? There's a rule. Triangle, I don't even know what it's called. But here's the rule, okay? Any two sides of a triangle have to add up to be more than the third side, or it doesn't make a triangle. Didn't we do that? Okay. Okay, just making sure that we talked about that. So this would not make a triangle, which means I just want you to know sometimes they're going to trick you, and they're going to say, does this make a right triangle, an acute triangle, or an obtuse triangle? Sometimes the answer is going to be it makes no triangle, because these two sides have to be bigger than the third side. Okay? So I just gave 3 examples. I really don't know what this is going to work out to be, because I just made these up. So it says classify each triangle, justify your answer. If you show work, kind of showing which theorem that matches up to, that's okay for justification for you. You don't have to write a whole paragraph about it. But for me, every time, one, I'm going to check that it makes sense, that two sides are all bigger than the other one for the triangle. And then I'm going to do Pythagorean theorem. I'm going to say c squared is what compared to a squared plus b squared. Right? Is it equal? Is it less than? Is it greater than? How do I know which one is c? It's the biggest one, right? So I'm going to say 15 squared. How does that compare to 9 squared plus 12 squared? Maybe you recognize this one. Maybe not. Maybe I'm not. Isn't this the 3, 4, 5 one? I get 225 equals 225. So if that's equal, what am I going to say? It's right. That is justification for me. Okay? Because that shows me that they're equal. Equal is right. So if you haven't already, start the next one. I'm going to do the next one too. You gotta remember to put c first if you're remembering less than, if it's greater than obtuse. And on number 4, I got less than. Did you get less than? So that means that I know if I drew that triangle, the equal requirement, right, that would be an acute triangle. What about the third one? Does it meet the requirements? No. It does, right? If I add two sides together, it's always bigger than the third side plus the third. Yeah. 14 squared plus 8 squared. So look, it worked out so nice. I think one of these, right? This one, c squared, is bigger than this side, which means that that is obtuse. Yes. Yes. So like on the one, if it was 1, 2, 3, that would not make a triangle because these two have to be bigger than a third one, not this. So I think that maybe you'll find it not as challenging as that.
Yeah.
The backside I did give you some story problems like number 8, number 9, draw a picture. Should be your right triangle. You should be able to do